In the second problem, we're asked some questions about motion of a pendulum. Let me point out one thing. Here's a pendulum hanging straight down. The pendulum moves along the arc of a circle. Now, if it's only moving from here to here, well, it's not moving along a lot of that arc, but it's still on an arc of the circle. Now, if the pendulum is, let's say, here, in what direction is it going to move once I release it? Well, it's going to move perpendicular to the string because the string is radial, and it's going to move along the direction of the curve, the direction tangent to the curve. So if it's here, I'm having trouble doing that with one hand, but it's going to move down slightly below horizontal. Now, if it's very close to its equilibrium position, there's almost no downward component to the motion. The motion is almost all in this direction. Pull it back a little further. That's still true, but not as true as it was. If we get out to here, then there's clearly a downward component to the motion at this point. And anytime we have it even the smallest distance from equilibrium, there will be a downward component of the motion because the circle doesn't remain horizontal. The tangent line to the circle is horizontal right here. Any other point, it's not horizontal. Pull it a little further back this way, it's going to be down below horizontal, even if only by a very slight amount. Now, so first thing we need to see is this picture. These pictures are a little crowded. Sorry about that, but the dotted line represents the vertical direction. We have a 20-degree angle, so we have a pendulum out here at 20 degrees. It's moving along the arc of a circle. Now, that arc isn't quite exactly the arc of a circle, but you understand that that could represent the arc of a circle, and that if the pendulum is released right here, in the initial instant after being released, its motion will be in the direction tangent to that circle, perpendicular to the radial line, the line from the center to the pendulum mass. So it's going to be a little below horizontal. Now, we're asked to do a free body diagram, and let me explain this. This says A or F net, either the acceleration or the net force, since the net force is mass multiplied by acceleration. And there's a little bit of crowding there. Let me fix that. Okay, either the acceleration or the net force will be in this direction. Now, we want to sketch a free body diagram. That's really pretty easy. The only forces acting are gravity acting downward and the tension acting in this direction. So right here is a free body diagram. We'll let the point represent the mass. We have the weight mg acting downward. We have the tension acting this way. Now, if we try to depict these vectors to scale, it's a little tricky to do that. This isn't a bad depiction, and this isn't a bad depiction, but neither one of these is probably going to be exactly right. To get it exactly right, we would have to have the net force vector come out in this direction. Now, if this is our picture, then we have our mg vector and our tension vector. Our resultant of the mg and the tension vector should be in this direction. However, if we take our mg and put it head to tail with the tension vector, so we just bring this vector over here, or we complete our parallelogram, we see that the mg vector is either a little too long or the tension vector is a little too short. Why do I say that? Well, that's again, okay, there's the vector, there's the vector. The resultant vector is going to be what we get when we go from here to here and back down to here. That's going to be the green vector. And that green vector is too far below the horizontal. It's clearly more than 20 degrees below horizontal. This one being tangent to this pendulum, to the string of the pendulum, which is at 20 degrees to vertical. This vector here, which is tangent to that, is going to have to be 20 degrees below horizontal. This is more like 40 degrees below horizontal. So this isn't a bad picture. Eyeballing it, you couldn't tell until you actually grab this vector and put it here. So this would be a plausible attempt at drawing the vector to scale, just like this is. But I believe mg is still too long here. If we put that together with the tangent vector, we're going to end up down here just about like we did over here. Now, if you draw the two vectors the way they're drawn here, just to be clear where those two vectors are, this vector is too short. If you put this together with your tangent vector, you get a net force in this direction. Not only is it not 20 degrees below horizontal, it's not even below horizontal, it's way above horizontal. This would not be a good attempt at drawing the vectors to scale. A good attempt at drawing the vectors to scale would be one where you actually had to take this vector, put it here, and construct it to see that it isn't right. This one or this one are pretty good attempts. This is not. This is clearly way too short for this. If you visualize putting this together with this, you don't even need to draw it. You can see it's just not going to give you a resultant at 20 degrees below horizontal.